X9 conservative force. Conservative, if a system involves forces that are conservative, then we have a very nice condition. The total mechanical energy, that is the sum of the kinetic energy and the potential energy. This quantity is conserved. That means conserved means its time derivative is 0. So this E of t, total mechanical energy at time t, is always the same as t, the value at measured at t prime, that is different from the original measured time. So independent of time, is conservative, is very important. So we have to know how to identify a force is conservative or not. To do that, we need to know these three operations. This f of x means this is a function of position. Function of a position in three-dimensional space is called field. It is not mathematical field, it is a physical field. The field means, application of field means gravitational field, electric field, magnetic field. These are field. It is different from mathematical field on which algebra is defined. We have a scalar field, a vector field. We remember gravitational acceleration is independent of position near the surface of the Earth, so it is a constant vector field. For example, we also have a field that is electric field, that is position, function of position, and its value is a vector. And we have a scalar function. What kind of example of scalar function is you find a map of the atmospheric pressure, high pressure, low pressure. If I write this, any point on this plane is expressed as x comma y, two-dimensional plane. We have a value that is called the pressure. So this is a scalar. Pressure is a scalar. So this map shows the how high, how low is the pressure at a given point. So we have scalar field or vector field. If you have a scalar field, there are three ways of taking the derivative. You learn from in high school to take the derivative, and you were allowed to take the derivative of a single variable function because you have been isolated on a straight line represented by a number line. But nature is not one-dimensional, not two-dimensional. It is three-dimensional space. So you learned in high school to take the derivative along a single one-dimensional case. However, in our life, we are living in the world in the three-dimensional space. So when I take the derivative, I need to consider all three directions independently. So if you erase these two and you are left with a single dimensional derivative. And usually when you learn this kind of first order derivative in mathematics class, they didn't teach you, they didn't allow to attach the unit vector along that axis because you are forced to live in the one-dimensional space. In that case, you didn't have to include the basis vector because the choice of unity and zero represents it is hidden in here. However, if I want to study physics in the three dimension, you fail if you keep using the one-dimensional approach. What you need to do is take the derivative along all three possible directions that nature allow you. Okay, so this is called the gradient. Gradient is x derivative and multiplied by the unit vector along the x-axis, y derivative multiplied by unit vector along the y direction, z derivative multiplied by the unit vector along the z direction. And your resultant one is, after the operation, what you have is a vector. Okay? This one says among the three coordinate variable, you fixed these two and vary x1 only. x2 partial derivative is keep this x1 and x3 and vary x2 only. In this manner, you can find the gradient. Next, we have to memorize what the divergence is. Later, you will study what the divergence is in the physical meaning of the divergence, but let's just memorize the definition. Divergence of a vector field A is x derivative of the first component, y derivative of the second component. You know, A has the x component, y component, and z component. The sum of the three components, and we just collect the Cartesian component, the first Cartesian component of the vector A, and take the x derivative. Second one, y derivative, and third one with the z derivative, and then sum them all. And this one is called the divergence. Divergence is very important to find whether a vector field is emitting from some point. For example, electric charge is there, that electric field is diverging from a single point. This operator shows that if it is the case, this divergence is positive, diverge. If the divergence is negative, it is sink. For example, negative charge, the electric field come into the negative charge, we say this divergence is negative. If a steady flow of field exists and there is no source or sink, then divergence of A equals 0. In physical meaning is that. Next one, we consider curl. Curl is a winding. Curl is a rotating. In nature, mathematics doesn't know why. Do you know why the magnet is generate a magnetic field? magnetic field around, you have a current I flowing along a direction, then magnetic field is generated. It is a physical fact. Mathematics, if you learn mathematics 100 or 1000 years, mathematics cannot tell you why the magnetic field is surrounding the current. That is physics. That is physics. Okay? So curl, this strange symbol, this delta cross vector field. This one shows this curly field is generated if this curl is non-zero. If this curl is zero, there is no rotating field, just like a magnetic field surrounding the current. So you have to remember, memorize gradient of a scalar field, divergence of a vector field, how to write, and you have to compute, and curl of a vector field. And you remember cross product of A and B. They are anti-commutative. If I exchange the order, it became minus B cross A, something like that. So they are anti-symmetric. Therefore, we remember Leibniz-Civita tensor representing the anti-symmetry property of the cross product. Just like the cross product, instead, I insert the operator. What operator? Gradient operator, just like what we have used, the gradient operator. Gradient operator, and substitute in here, and then take a cross product. Then you remember when I compute A cross B, E to the first component is A2, B3, A3, B2, E2, A3, B1, A1, B3, and so on. Just replace this one with the derivative operator. X2, X3, X3, X1, and so on. So we have negative sign when I exchange 3 and 2, 3 and 2, 1, 2, 3, 1, 3, 2, minus 2, 3, 1, 2, 2, 3, 1, 2, 1, 3. They are mutually odd permutation. 3, 1, 2 plus, and 3, 2, 1 minus. So you have to remember how to compute the gradient, divergence, and curl. Gradient, 1 over r. R is the x squared. X is a position vector. Why don't we define this x squared? We define by capital X. Then we'll have a gradient operator, and 1 over r is 1 over square root of x, 1 over square root of x. And then you apply chain rule. Well, how? I would like to take the derivative with respect to x1, but this is a function of capital X. So I first take the derivative with respect to capital X, and then I take the derivative of capital X with respect to X and Y and Z. X and Y and Z. And then I have to multiply the unit vector E2, E2, and E3, E3. By the way, this is x vector squared is x squared y squared z squared. So if I take the derivative with respect to x, what I have is only this component. Derivative, partial derivative with respect to x kills everything that is independent of x. Therefore, this one is 2x, this one is 2y, and this one is 2z, right? And then this derivative is nothing but this. 1 over square root of x is actually minus 1/2. So this factor appeared, and then I take the derivative, so I added minus 1. That became, in the denominator, 3/2 power for the capital X. So finally, these 2 cancels. And what's that? This is a square root of capital X cubed. And square root of capital X is nothing but R. So R, this is R squared, and this is R. So R cubed. However, we have numerator, this vector. What's that? This is E1, X1, E2, X2, E3, X3. That is nothing but X vector. X vector divided by R, and R is the magnitude of X. Therefore, this is a unit radial vector. As a result, our gradient of 1 over distance from the origin is unit radial vector divided by R squared, and we have negative sign on it. It is a very, very important. We keep using this result in the future, in the next semester too. You cannot avoid. Explain the properties of a conservative force. Memorize conservative force is applied, and if you follow a closed path, this closed, this is C is the curve, and this is circle represents a closed curve. If you do some work along a closed path, regardless of the shape of this curve, it is a vanishing. That is the definition of a conservative force. Next, if there is a potential energy that is a function of a position only, and if it is a force is expressed as a gradient, minus gradient, that is very important, negative gradient of a potential, then it is always conservative. Memorize. Third one, f times dx, because if it is conservative, it is expressed as a minus gradient. You remember, gradient is what? You partial derivative with respect to x, y, and z. And what is dx? Dx is E1, dx1, E2, dx2, and E3, dx3. If I take the scalar product, this one, this one, this one, the final result is this. You are familiar with the one-dimensional chain rule. One-dimensional chain rule. However, we have function u that is simultaneously function of x, y, and z coordinate. So the differential, you have df over dx. If you know this, in one-dimensional case, then everything is fine. And what is that? That is just g is the derivative of f with respect to x. By the way, if we have three different independent variables, how can I compute this differential? This is the generalization of this one-dimensional case. Our answer must be of the form and we neglect the higher order piece in the infinitesimal limit. Therefore, this one, in one-dimensional case, that was just nothing but df over dx. However, we have to vary x1, x2, and x3 independently. Therefore, this f1 is partial derivative of f with respect to x1. This one, partial derivative with respect to x2 and partial derivative with respect to x3. This is the multi-dimensional generalization of chain rule. Okay, so because of that, we can combine everything all together. This is nothing but the differential of u. If it is differential of u, integral is trivial. Why? Integral dx, do you know this? This is x. There is nothing to compute. And if it is an integral from a to b, and the answer is a to b and b minus a, you find that this kind of total differential is the definite integral that is independent of a middle point, the independent path, and it is depending only on the upper and lower limit only. That's the reason why the work done by a conservative force along a closed path is always zero. So all three things you have to memorize. In addition, you have to memorize this. Your brain must have a carbon copy of this. We'll keep using this relation that is called Stokes' theorem. Complete proof is given in the corresponding X version, but I don't want to review all the details about the Stokes' theorem's proof. We do not need that, even though I have provided it. So you just remember the result, and you have to be able to apply this result in a correct way. Let me tell you, F doesn't have to be a conservative force. F is an arbitrary vector field. But any vector field integrated over a closed path, this circle is a closed path. If you integrate over a closed path, final result is the same as what kind of integral? This right-hand side is an integral dividing the surface. This is a boundary, and this from right-hand side is integral over a surface surrounded by this closed path. With this we call S, surface. And we use boundary of surface is the path C. So we have this sigma. This sigma has the magnitude of this area and direction is perpendicular to this plane. So this one represents this sigma. And what we just have seen what the curve is. Curve is not vanishing only if this vector field is rotating. In effect, this curve is not vanishing only if rotating. So if I divide into many pieces, this curve, they cancel in the middle and only on the boundary is left. Therefore, this right-hand side surface integral collapses into a line integral along a closed path. And at the end of, oh, not this, at the end of X9, you will see the second, this two-dimensional version proof called Green's theorem. Okay. However, you will learn in calculus class, but perhaps at the end of this year, but it's too late to study physics. So you will learn later, but you have to make use of the result. So I don't ask you to memorize all the details of about the proof, but I ask you to memorize the theorem itself. Don't ask me how to prove. It is given already, and 1 year later, you will learn in mathematics class. Stop talking about how to prove this, okay? The freshman students keep asking me both the physics and mathematics. I'm physics teacher, okay? A scalar field U exists such that, okay, this is what we already have shown. Irrotational is called when the curve is 0. If f is irrotational, curve is 0. This integrand is 0. Aha! So it is exactly 0. Exactly 0. Scalar product. So it is not a vector, it is 0. Aha! If we can compute the curve of a vector field, and if it is exactly 0, I can immediately obtain that f's integrated over a closed path is exactly 0, whatever closed path you may give me. So it is very simple. So computing a curve is very, very important. Usually what we study is vanishing, for example, magnetic field, this electrostatic field. Magnetic field does not. Electrostatic field, it is a 0. And the magnetic, not gravitational field, it is a curve is a 0, that they are irrotational. Magnetic field is rotating around a current. But current is a moving electric charge. So electrostatic means all the charges are all stop. They do not move at all. Then there is no magnetic field and no current. There exists a potential energy U satisfying. Okay, you can find appropriate scalar field whose minus gradient is the same as the given force, then that's fine. Then everything is done. So this, we usually use this, and sometimes we use this. And we are keep using this everywhere this semester and next semester too. Okay, what you get by taking the time derivative of the work kinetic energy theorem. Work kinetic energy theorem is work F dot dx integral is the work. Work is the difference change in the kinetic energy. That is the work kinetic energy theorem. We take the time derivative. In here, we know how to take the derivative. What's that? We have been doing this kind of calculation so many times, I don't have to repeat this. Next, this one. Why don't we make use of chain rule? This integral looks implicit, but actually that endpoint is x, and this integral is over some primed variable that's integrated out, and some starting point is given here. We don't have to worry about this lower limit, but upper limit is important. This x is E1 x1 t, E2 x2 t, E2 E3 x3 t. So they x1, x2, x3, all of the Cartesian components are time dependent. Therefore, why don't we make use of chain rule? Because this is not a number, but a function of coordinates. So I first take the partial derivative with respect to x1, x2, and x3. But eventually I have to take the time derivative. Okay, come on, take the derivative. Come on, take the derivative. Come on, take the derivative. This is the three-dimensional generalization of the chain rule. And this is nothing but the scalar product of what? Velocity and the gradient. This is a gradient, what we learned just before. Okay, gradient. By the way, what's that? Minus negative gradient. Is there any function that is the negative gradient of function reproduces the force? Okay, let's see. Pull out the negative gradient, and because it was just a simple gradient, I insert this negative side inside the parentheses. What I obtain is, okay, this is my negative of gradient, Okay, this is potential energy. Let me say this is the work, and why don't we express as this is the work, and I define this work by negative of a potential energy. And what's that work? Kinetic energy theorem says that the kinetic energy change is the work. Why don't we move this one to the left-hand side? That is delta t plus delta u equals 0. Aha, work kinetic energy is rewritten by just flip the sign of the work by negative work to define the potential energy. Then this is a trivial carbon copy of the work kinetic energy theorem to arrive at the total mechanical energy conservation. And finally, we have found that the potential energy is just a negative work. That's it. And then potential energy is a force. That's it. And then we have a common factor velocity, and the time derivative of kinetic energy is the, what's that? This is the force scalar product velocity. Force scalar product velocity reproduced, they are the same. So force minus mx double dot. Because of this, we began with this work kinetic energy theorem. Work kinetic energy theorem doesn't say anything but equation of motion. That is Newton's second law. And you can, I can briefly review this. If you are given some force, you are asked to compute the potential energy, but integration is more difficult than take the derivative. You find the gas. You have minus kx, that is a minus x derivative of potential. Why? I told you F equals minus the gradient to U, and you are looking for U. That gives this force. What is the potential energy to reproduce this? At least this is Kx. You have X derivative. You expect that it should be K something squared. And if you take the derivative of this with respect to X, you will find 2Kx. Aha, we have a factor of 2 mismatch. So final result is 1/2 Kx squared. To reproduce this, what's next? This is Ky. Aha, if it was Kx squared for the X component, then Y component, it's trivial. So 1/2 Ky squared. Without complicated calculation, I can write down this 1/2 Kx squared, 1/2 Ky squared. You can say that just the x squared plus y squared. Try this and find out the coefficient appropriate to reproduce the force is minus gradient u. In addition, this u, this gradient applied to a number, for example, gradient 1 is a zero vector. Any constant on the gradient operation, any constant vanishes. So you have a freedom to choose arbitrary constant number to a potential energy. However, if there is some condition that potential energy vanishes at a certain point, then you just substitute these values in the formula and determine what this C is. As soon as you determine this constant, then just substitute to the original form to find it. But anyway, this one doesn't matter too much unless you are computing the total mechanical energy with a certain representation of the potential energy. In that case, this constant is very, very important. 7, another application. I think there is no big problem without in solving this. This one is for electric charge or mass, uniform mass distribution that generates the electric field or gravitational field. We are living on a spherical surface that is called Earth, but theoretically we can think about the discharge mass distribution along a straight wire. We do not have such kind of astronomical object, but so we can make some theoretical assumption. Anyway, if the mass or charge distribution is a symmetrical of the three-dimensional space, the electric field or gravitational field is weakened by a factor of 1/r squared in 3 dimensions. That is called inverse scale law. However, if it is along a infinite straight wire that carries a uniform charge over uniform mass, then one dimension along the z-axis disappears. And this one, although this happened in 3 dimensions, effectively it is just like the 2-dimensional problem. You know, this 1/r squares came from the fact the area of a sphere of radius r is proportional to a radius. This is volume. Surface is a 4πr squared. And what is the boundary of this? 2πr. So that's the reason why it is spherical or point like mass or charge distribution will give the electric field attenuating with a factor of 1 over r squared. But in case it is a infinite straight wire, then the strength is weakened, not proportional to 1 over r squared, but proportional to 1 over rho. This rho is a planar, the perpendicular distance from the center. This is a cross-sectional view of this three-dimensional space. And this is a detailed calculation, so you can follow that. Okay,